Good morning, students. Today we are going to start section 4 of partial differential equations. In this section, we will discuss different ways to represent the solutions. So our first topic is separation of variables. The method of separation of variables that tries to construct a solution to a given partial differential equation as some combination of functions of fewer variables. It means if we take u as a function of variables x and t, then that can be written as sum or product of the functions. We have taken two functions here, one function v, which is the function of x, and second we have taken w, which is the function of t. So according to our convenience, we can take u as a sum of functions or the product of functions. We will discuss this method in detail. So first of all, let us discuss what is eigenvalue of the operator minus del. Here del is Laplacian operator that we have already discussed. So let us define its eigenvalue. Let us take U is an open bounded subset of n-dimensional real Euclidean space. Then we say that lambda is an eigenvalue of the operator minus del on the set U, subject to zero boundary conditions, provided there exists a function w which is not identically zero, and solving the problem minus del w is equal to lambda into w in the set U, and on the boundary of set U, the value of function w is 0. So if this condition holds, we see that w is the corresponding eigenfunction for the eigenvalue lambda. Now let us discuss first example for the method of separation of variables. We will solve a problem for the heat equation. So let us define the boundary value problem for heat equation. Let us take U be a subset of Rn. Rn means n-dimensional real Euclidean space. This U is open and bounded. Consider the boundary value problem for the heat equation. Partial derivative of U with respect to t minus Laplacian of u is equal to 0 in u cross open interval 0 to infinity, with the conditions that the value of u is 0 on the Cartesian product of boundary of u with semi open interval 0 to infinity. When time is 0, the value function u is g, means the value function u at the point x comma 0 is g. G is the function of x and x is belonging to u. Here g is a real valued function defined on u, and this is a non-function. Now let us find the solution of this boundary value problem by using method of separation of variables. Let us take u, which is the function of x and t, that is a solution of equation, solution of this boundary value problem, having the form v into w, where v is the function of t and w as a function of x. So we have written u as a product of two functions in which one is the function of variable t and another is the function of variable x. Now because u is the solution, so that will satisfy this equation. So let us find the values of del u and ut from here and substitute there. Now differentiating both sides partially with respect to t, the derivative of u is denoted by ut. Here t is in the base and denotes curl u by curl t. Here, because only v is the function of t, so its derivative with respect to t, that will be v dash, and this will be as it is because we are taking partial derivatives with respect to t. Now Laplacian of u. Now Laplacian is taken with respect to the variable x. So this term will remain as it is, and we have Laplacian of w. So we get Laplacian of u is equal to v into Laplacian of w. Now we can substitute these two values in the heat equation. Heat equation is ut minus Laplacian of u is equal to 0. Putting both values, we get v dash t into w minus v into del w is equal to 0. Now separating the variables in t and x on the different sides. On the left side, this is a function of t only, and right side is a function of x only, and both expressions are equal. So this is possible only when both of these expressions are equal to some constant, because they are the functions of different variables. So they can be same only when both of them are constants. So let us take both of these expressions are equal to the constant mu. So from here we get v dash upon v is equal to mu, and Laplacian of w upon w is equal to mu. Now integrating from here, we get log of the function v is equal to mu into t plus some constant a. Removing log from both sides, taking exponential function here, we get v is equal to e raised to the power mu t plus a. Now we can write this term as e raised to the power mu t into e raised to the power a. Let us denote e raised to the power a by b. So we get the value of v as a function of t, which is given by b into e raised to the power mu t. Now let us use the boundary conditions which we are given in the problem. We are given that the function u satisfies, because we have taken u as the solution of given boundary value problem. So that will also satisfies the boundary conditions. The first condition, we are given that value of u is 0 on boundary of u cross semi-open interval 0 to infinity. Now the value of u is v into w. So v into w is equal to 0. Putting the value of v from here, we get b into e raised to the power mu t into w is equal to 0. Now this term cannot be 0. So from here we get w is equal to 0 on boundary of u cross semi-open interval 0 to infinity. Thus we have from here we are having Laplacian of w is equal to mu into w in the set u, and on the boundary of u the value of w is 0. So by definition of eigenvalue of the operator minus del, we can say that minus mu is an eigenvalue and w is the corresponding eigenfunction. Now let us take lambda is equal to minus mu. So finally we get the value of u as a function of x and t, which is given by b into e raised to the power minus lambda t into w, which solves the problem ut minus del u is equal to 0 in u cross open interval 0 to infinity, with the condition value of u is 0 on the boundary of u cross semi-open interval 0 to infinity. Now it remains to use the last condition which we are given in the problem, that when time is 0, value function u is g. Now let us apply that condition. Now the value of u when time is 0, we get this is b into w, and according to the given condition the value of u when t is 0 is g. So we get g is equal to b into w. From here we can find the value of w, which is given by g upon b. Now finally substituting this value of w in the solution. The solution of the given problem is u, which is the function of x and t, and that was the product of two functions. One of the functions was v, which is the function of t, and another is function w, which is the function of x. The value of v we have already obtained as b into e raised to the power minus lambda t, and value of function w from here, which is g upon b. Now b is cancelled out from here, so we get the value of function u as a function of x and t, and finally it is given by e raised to the power minus lambda t into g. So this is the required solution for the given boundary value problem for the heat equation.